Hi everyone and welcome. This is chapter 14 of the DB2 course. We are talking about query optimization. Alright, so the last video introduced the abstract cost model and its cost model parameters. So based on that cost model and based on these cost model parameters, let's look at the sequential scan operator in this particular video and try to derive a useful cost model, a cost estimate for the sequential scan operation. We will do something similar for the somewhat more complex index scan operation in the upcoming and last video. Okay, so given that a plan features a sequential scan operation, so the sequential scanning of all the pages in a heap file, what would be the abstract space dollar cost value that we would assign to that? Of course, we would expect that parameters of the cost model like the sequential page I/O cost or the CPU operator cost, all of these we expect to influence the space dollar cost value that we will have to compute. All right, so let's make that more concrete here. We are given a plan in which a sequential scan operation occurs. Of course, that sequential scan will be executed over a given input table, all right? And we will see that the system can look up its own metadata, its catalog tables, to collect information about the input table. For example, the cardinality of that input table, the width of the rows, and how many pages have been allocated in the heap file for that input table. All of this will influence our cost computation. Then such a sequential scan normally is equipped with a predicate that might be optional, but in the examples that we will look at, there will be a predicate filter that is applied to all the incoming rows. And we expect that there will be some CPU cost, at least, for the evaluation of this particular filter predicate. There are simple filter predicates like this one maybe. There might be more complex Boolean expressions. And well, you could expect that a more complex Boolean expression would influence the cost model and would drive it up, or would drive the space dollar cost up. Okay. Right, and then likewise there is the output expression, the expression that is being computed on all the rows that could pass the filter. Well, in this very simple plan, this output computed by the sequential scan already is the query's final result, so the query will only emit a single column that will carry this computed numeric value here. But in general, well, the sequential scan would pass these computed output values, these expressions that have been computed, onto their parent operators. All right, so if you look at such an explain plan, of course it will have startup cost and it will have total cost, and this is actually in focus here. Well, we will also talk about startup cost, but we would in particular derive the total cost of the sequential scan operation. This will later be used to compare this variant of the access to the indexed table. In this case, it's the index table, the input table. We will use the total cost to compare this access to the indexed table with other possibilities and options to access the rows in indexed. And well, if that space dollar cost, these 22.75, are the cheapest value, then probably we should choose sequential scan to access the rows in indexed. What we will also see is an estimate of the size of the output that will be generated by the sequential scan. In this case, it's again the cardinality of the overall result, but otherwise this will be an estimate of all the rows that will be piped using the volcano iterator model into the parent operator. So how exactly do we derive startup cost and total cost? All right. Well, the cost calculation for sequential scan depends on a number of parameters that, of course, parameters in the cost model configuration that we've seen in the previous video, but also parameters that are of course dependent on the particular input table that we are processing and the particular expression and predicate that we are processing. Most of this information can be collected, as I said already, from PostgreSQL own internal catalog files held and exposed in the metadata tables that start with this prefix PG underscore. We have looked at many of these already, and well, these become relevant in this context again. So we will see that the cost model formula that we will use to assess the cost of sequential scan will in particular look at the cardinality of the input table, so the number of rows that we can expect in the input table. All right, and well, there is one particular class in table in the meta level of PostgreSQL that the PG underscore class table that we can query. Its column rel tuples will inform us about the cardinality of particular tables. For example, the indexed table that we query over in our sample query. Likewise, we can check for the number of pages in the heap file for this particular input table. Right, and this is to be collected from the rel pages a column in the PG underscore class table. Well, we will briefly switch over to the terminal and then check that indeed all of these parameters are set and that they have sensible values there. And then there's also the predicate selectivity, the pickiness of the predicate that we are evaluating during the sequential scan. How many rows will pass this particular predicate, and how many rows will thus have to be, well, processed regarding the output expression, and how many rows will have to be passed on to consumers of the output of this sequential scan. This is known as the selectivity, and it's a number between 0 and 1, right? So if that number is 0, as you can see here down in the footnote, if that number is 0, the selectivity indicates that the predicate is so picky that not a single row will survive it, probably. And selectivity of 1, which would be the other extreme, would indicate that the predicate lets every row pass, and there's actually no filtering behavior assigned with that predicate. Normally you would find a value between 0 and 1. The lower the value, the more picky the predicate becomes. All right. Values like the rows in value or the pages in value, so metadata about the particular tables, are brought up to date whenever we perform an analyze run on these particular tables. Right, so now and then it might be useful to set some time aside and have the system focus on updating its own metadata information. As you can see, well, this up-to-date information will lead to plans of better quality in subsequent queries. So it might be time well spent when we run these analyze calls. All right. Well, we will not talk about the estimation of the selectivity of a particular predicate in this particular instance of the DB2 course. That's very interesting in its own right. It's a mixture of an estimation that is based on sample data that we have extracted from the underlying tables, so that we are informed about the typical value distributions in the individual columns of our tables. And well, also the syntactic structure of the predicate will go into this selectivity estimation. So a conjunctive predicate will have a different selectivity than a disjunctive predicate, for example. And well, this is interesting in its own right, and would take some time to discuss here. No such time in this particular semester, but you will find plenty of material also in earlier instances of my DB2 course. Just search my web pages and you will find a discussion about the selectivity of predicates. Alrighty. Okay, so let's see how we can combine all of these ingredients to arrive at cost formulas, or space dollar cost formulas for the sequential scan operator. And this would fit on this particular slide here. In the case of sequential scan, it fits on one slide. In the case of index scan, we will have to develop more intricate formulas. But for sequential scan, I think it's rather easy. So let's look at the startup cost for sequential scan first. Well, the startup cost in this case incorporates the startup cost of the predicate and the expression in the output of the sequential scan. So we would assess the startup cost for these two ingredients of our sequential scan, and since these are rather simple expressions in this particular case, they would be assigned a startup cost of 0. So these expressions, they would be ready to process the first row immediately. There would be no initialization cost or whatever involved with the evaluation of such expressions. We will later see an example where the startup cost of a predicate, for example, will not be 0 because there's some computation to be done before we can evaluate the predicate the first time. But in this particular case, or in the general case, you will often see that the startup cost of such expressions is indeed 0. All right. Well, if we've got the startup cost, that's already good. To derive the total cost, what we now need is the run cost of sequential scan. So the actual time spent during the evaluation of the sequential scan. And as you can see, we divide this run cost in CPU part and in a disk I/O part. Both together will make up the overall run cost of sequential scan. So CPU run cost and disk run cost are assessed here separately, individually. So let's look at CPU run cost first. Of course, this models the effort that the CPU has to invest to evaluate the predicates and the output expressions for all the rows that have to be processed. Here is the number of all the rows that have to be processed. This is the number of input rows that will be processed. For each such input row, we will have to invest some CPU effort to decode that particular heap row. We will have to navigate into the particular fields that are relevant for the evaluation of our predicate and expressions. There is some decoding to be done. And well, this is accounted for with CPU tuple cost. For each row that we read, we will invest CPU tuple cost. But that's not all. For each of the incoming rows, we will also invest the run cost of the predicate. So we would have to dive deeper into the predicate and see how many operators, how many comparison operators, how many Boolean operators are actually involved in the evaluation of the predicate, and thus assign a run cost to this particular predicate. We will see in the PostgreSQL terminal, when we look at a concrete example, how this run cost turns out for one given predicate. So that would account for the evaluation of the filter predicate for each of the incoming rows. So all of this here in the first row would account for the cost that we face because the incoming rows have to be processed. To this, we add the effort that we have to invest to process the outgoing rows. Well, there are less outgoing rows in general than there are incoming rows. That's because, well, the predicate will probably throw some of the incoming rows away. How many of these incoming rows will be thrown away? Well, the selectivity of the predicate will tell us. Right, so this multiplication here, the rows in times the selectivity of predicate, is indeed the cardinality of rows that we will emit, that we will produce and then send to the output or submit and ship to all the parent operators that consume our output. So that would be the cardinality of the output. For each such row that could qualify regarding the predicate, we will have to run the output expression. All right, so there will be some run cost involved in the computation of the output expression, and well, we multiply these costs for each row that will be sent to the output. So that would be the CPU cost that we will face. And how about the disk run cost? Well, we would have to read the pages of the incoming file, right? This would be the number of pages in the input table. And well, we will sequentially scan the heap file associated with that input table. So we will read that many pages in sequential fashion, and thus will face sequential page cost for each of the pages in the input heap file. And that would be the disk run cost already. All right. Okay, so the sum of the run cost, CPU and disk run, and the startup cost, well, both together make up the total cost of our sequential scan operator. Well, if you now complain that there is a number of intricacies and details that are not reflected by these cost formulas, then that's probably true. This is an abstract cost model that tries to capture the most essential, the most significant influences on the evaluation time of sequential scan, nothing else. All right, so now it's time to switch over to the terminal. Let's do that. Yep. There we are. All right, so this is an experiment that is also performed on our playground database. So what you see here is that we are querying our index table. There are no indexes involved in the query that we are performing right now, but there will be indexes involved in upcoming queries. All right, but well, you know the index table. I have already recreated it in my Scratch database. I've also analyzed it. Let's analyze it again. All right, time well invested, so we can now expect that all the metadata tables, the number of rows, the number of pages, and all other interesting metadata about the index table is now up to date and is properly reflected in our PG underscore metadata tables. This is the index table. Just to remind you, 3-column table, nothing but the primary key B3 index on the A column here. All right. So now let's check for the metadata of the indexed table. For example, the number of rows and the number of pages that it occupies on disk. All right, so 1 million rows and 9,346 pages currently in the heap file for the index table. Both parameters will be input to the cost formula, to our cost estimation for sequential scan. And well, here's our sequential scan. It's a very simple sequential scan. This is the most simple expression that we can probably think of. There is no arithmetic involved. We just reproduce the A column value. There is no filtering involved. It's just a sequential scan over the index table. All right, so let's do an explain verbose here. It's just an explain verbose, no analyze. So what we see here will be cost values that are estimated according to the cost formula inside PostgreSQL. All right, super simple plan, sequential scan, no filter predicate. The output is just the unaltered column A. And well, this is the cost value that is being assigned. A startup cost of 0. I think we have expected that because we said that there would be a startup cost of 0 involved for the predicate and the expression. Well, we see that here. There's indeed a startup cost of 0, but an overall total cost of 19,346. Let's see how the system arrived at this particular cost value. So let's resize the window a bit here, because now the interesting stuff happens here in this SQL comment actually, which would be just a repetition of the cost formula that you've seen on the slide, but now instantiated with all the concrete values that regard our table index, for example. All right, first for the startup cost. The startup cost of sequential scan, well, will simply assess the startup cost of the predicate and the expression. Both are 0, so we end up with a startup cost of overall 0, and this is exactly what we see here. All right, now for the run cost, which would be divided into CPU and disk run cost. Okay, so this is just the formula from the slide regarding the CPU run cost. All of the incoming rows, we have to decode these rows and we have to evaluate the predicate. and well, all of the outgoing rows. This is the number of outgoing rows. For those, we have to evaluate the output expression. Right, so well, we simply instantiate. These variables here. There is 10 million input rows. For each of these, we will have CPU tuple costs, which are 0.01 if you look at the default cost model parameters that we've seen in the previous video. The run cost of the predicate is 0 because there simply is no predicate to evaluate here. All right, and then regarding the outgoing rows, well, there will be 10 million outgoing rows. The selectivity of the predicate that is implicit here, where true predicate, well, the selectivity of that predicate is 1. Every row can pass. So indeed, we will emit 1 million rows here. And well, there is simply no effort in evaluating an output expression at this particular point. The run cost of the expression is indeed 0. It's just the reproduction of the A column value, which we have decoded anyway already at this particular cost here. And well, there is just no additional CPU effort to invest in the evaluation. Right, so the CPU run cost then amounts to 10,000 space dollars. All right, so how about the disk run cost? Well, that would be the sequential page cost that are incurred for each of the pages inside the heap file of our index table. There are 9,346 pages. Let's recall. Yeah, all right. Each of these will incur a cost of 1.0, which would be the default sequential page cost value. Well, that ends up and leads to 9,346 space dollars. If we add all of this up, we end up at the overall total cost of 19,346, and which is indeed the value that PostgreSQL reports here. This is the cost of a super simple sequential scan. Right, so let's complicate things a bit here and well, have a sequential scan without a filter, but now there is a predicate that is somewhat more interesting. There is some arithmetic involved, a multiplication by 2 here and then the addition of 1. You will see that the cost formula reflect the syntactic structure of this well, more complex expression, and there will be some CPU effort that needs to be invested for the evaluation. Okay, let's see. All right, indeed, the estimated space dollar value has increased to now read 24,346. All right, so now we would follow the same procedure. We would assign assess the startup cost. There is no predicate. There is a very simple expression. Well, the expression has become more complex, but there is no initialization cost for this particular expression. There's no startup costs involved. The startup costs remain at 0. Okay, then there would be the CPU run cost. Okay, everything remains the same, but when we instantiate this particular formula, there will be a non-zero run cost in this particular case. Indeed, if we follow this particular formula, this would be the non-zero run cost. You see that it's comprised of 2 times CPU operator cost. Right, okay, the run cost of the expression is 2 times CPU operator cost. This is the CPU operator cost default value taken from the PostgreSQL cost model. Why 2 times CPU operator cost? Well, because there is a multiplication and there is an addition involved in the evaluation of this particular expression, the output expression. So 2 operator invocations make up for 2 times CPU operator cost when it comes to the run cost of the expression. All of this amounts to 15,000 space dollars. The disk run cost have not changed. They remain at 9,346. Adding all of this together leads us to 24,346, which coincides with what PostgreSQL estimated at this particular point. So I think our abstract cost formula that we have developed on the slides, I think it meets the internals of PostgreSQL quite closely. All right. So now we enter the world of sequential scans that have a filter. All right. So here's our next sample query. Well, everything remains the same, but we add this filter expression. Okay, so the run cost of this particular filter expression will be non-zero, and of course there will be a selectivity for this predicate that won't be 1. Right, to make sure that the system indeed performs a sequential scan here and doesn't try to be super clever, let's switch off all the other forms of scans here. All right, so now the system will use sequential scan. These commands set the startup cost of the index scan and the bitmap scan in the system to the ridiculously high 10 to the power of 10, and they won't be considered at all for that reason. All right, so let's look at the plan and the cost estimate for this simple query here. All right, it's still a sequential scan, and of course it will now evaluate a filter predicate, and it will also evaluate the same output expression. This is the cost that is being assigned here. It's 22,365. All right. This is the estimate of rows. The estimate of rows that the system estimates to pass this particular predicate. Well, there's 1 million rows in the index table. About 10% of these are estimated to pass the particular predicate. As I told you, this estimate is based on a sampling of data from the index table and also the syntactic structure. In this case, it's very simple syntactic structure of the predicate here. All right, so well, we could now invoke our cost formula again, and I will actually do that, but I will use a particular tool for that. It's an interactive calculator that I brought with me here. All right, so in that interactive calculator, I can play with all the cost model parameters, for example, that we have that we've already introduced in the last video. So what you see here, these variable assignments, they just reflect the default cost model parameters that are active in PostgreSQL right now. All right, to assess the cost of this query, actually I've reproduced the query below here. Okay, to assess the cost of this particular query, we would need information about the number of rows that are in the input table. It's 1 million rows, as you can see here, and the number of pages that are allocated in the heap file for that input table. If you recall, these are 9,346 rows. All right. So this is just the reproduction of the query. Now we could start our cost computation. What we would need is information about the number of estimated rows to model the selectivity of the predicate. All right, so I've got one estimated output row number here from a previous run of the query. The estimate has not changed. Let me enter the current estimate here. It was so about 10% of the rows did qualify regarding the selectivity estimate. All right, so the estimated selectivity, indeed, this is what the system would derive, and from that and from the input rows, it would of course derive this output value here. All right, so that would be the selectivity of the predicate. It's 0.1, and well, that reflects the fact that indeed about 10% of the rows will probably qualify against this predicate. All right, so now all the input parameters are there. Perfect. We can now instantiate our cost model. Well, we would start with the startup cost for the predicate and expression. These remain at 0, as we've discussed before. And well, the startup cost of the overall sequential scan operator will thus indeed also be 0, as you can see here. All right. Now for the run cost for the predicate and the expression. Well, we have seen the run cost for the expression before. This is an expression that features one multiplication operator and one addition. So the run cost for the expression was assigned 2 times CPU operator cost to reflect that there is multiplication and addition. The run cost for the predicate is now non-zero, it would be, well, it would be the cost to evaluate the less than or equals predicate, which occurs inside the predicate. So that would concur one time the CPU operator cost. So that would be the run cost of the predicate and the expression. I think this is all we need to already assign the CPU run cost. And all of this, what you see here is just copied from the cost model that you've seen on the slides and also seen over in the editor. It's the number of incoming rows, which we have to decode, and we have to run the predicate over these rows. Okay, here we can see that the run cost of the predicate indeed becomes relevant, and then there will be a number of output rows. This is a number of output rows. For those we have to evaluate the expression. Okay, that would be the CPU run cost, and then there is the disk run cost. All of this is unchanged. But if we add all of this up, we end up at a total cost of 22,365 space dollars. And well, let's switch back to the terminal here. And as you can see, this is exactly the value that PostgreSQL derived in this particular case. So also the presence of predicates is being reflected by the cost model formula in the correct way. Right, so we could now play with all of this and, for example, increase the CPU operator cost because, well, maybe we have underestimated the cost of the evaluation of operators in our system. Maybe it's 10 times as costly. And that this will of course have an impact on the overall cost estimate, which would be significantly higher now. All right, so CPU cost really makes a difference in a query that is as simple as this sequential scan query. So let's quickly change this back, otherwise we will be confused in subsequent runs here. All right, so as a final example, let's look at a query where the predicate looks a bit more daunting, a bit more complex here. Everything remains the same. Well, actually, we have switched back to a very simple expression here. But as you can see, the predicate involves a subquery. All right, this is a scalar subquery in parentheses. To make this a valid query, we expect the system to evaluate this particular subquery here and arrive at one numeric value, which we will then use for this outer query to filter rows. All right, so let's see how this is being planned, and then how the cost estimate looks like. Okay, this already took some time. Well, this is a more complex plan. Okay, as you can see, well, the plan in fact is still a sequential scan over the index table as expected, and there is of course the computation of the output expression. Let me scroll up the query here, and there's of course the computation of the predicate. All right, and as you can see, the this $0 sign here represents the numeric value that was derived through the evaluation of this subquery. Okay, so there is a part of the plan, this so-called init plan number 1 here. There's part of the plan which is to be executed and will return or will instantiate this $0 value. This will be a numeric value once init plan 1 has been performed, and will be placed here. And once we've done that, we are faced with well, with a rather normal sequential scan operation. Okay, right. Well, you can see how the init plan looks like internally. It's a simple scan over the index table again, and of course we would be computing an aggregate value here. All right. All right. So let's see whether our cost formula hold up here in this particular case. Well, we would first look at this rather complex predicate here. We expect the startup cost of this particular predicate to not be 0. There is effort to be invested. namely the effort to evaluate this particular subquery, before we can start to process the first row of this outer query here. The subquery is performed and evaluated before the evaluation of the first row of the top level query can start. So there will be significant startup cost. Okay, so the startup cost for this rather complex predicate is indeed the run cost that we will see for this subquery. All right, and well, I've assessed that and found that well, the run cost for this particular subquery is 21,846. Let's see whether we can see that. Yes, there we are. All right, so we will not look at the derivation of this particular value. We will simply accept it. So this is the time that we have to wait until the aggregate, the average value has indeed been computed. This makes the startup cost for the predicate of our top level query. The run cost is simpler to assess because once we have invested this initial subquery evaluation cost, this is just $0, as I've already shown you. This is just one computed numeric value. So the run cost for this particular predicate are simple to assess. There is just the comparison operator, the equals, equal or less than operator. Let's have a closer look at the filter. And then there is one additional operation, the cast to numeric. This is also using CPU time, and it's assigned the same CPU operator cost as the evaluation of any other operator. That's why you see that the run cost of this complex predicate is indeed 2 times the operator cost. 2 times the operator cost, CPU operator cost is just this default value. All right, so that would be the startup cost and the run cost of this predicate. What about the selectivity? Well, this is not so easy to assess for the system because when the query is planned, the $0 value, the value of this particular subquery is simply unknown. So, well, of course, this value is essential for the estimation of the selectivity. A very low value here will lead to high selectivity. A high value will lead to low selectivity. So, well, that's a problem here. We cannot afford to evaluate this particular subquery while we plan the query. So, well, the system has to assume some default, some arbitrary selectivity at this particular case. There are some heuristics baked into the system, and as we can see here in the estimated row output of our query, well, the system simply assumed that every third row can pass the predicate. In the absence of any further information, well, the heuristics say that every third row will be able to pass that predicate. Right, so, well, this is the selectivity. It's just 0.3.3. In this particular case, the system may be more clever, right? This is a comparison on the A column. We are comparing with the average of the A column, right? So, well, the true selectivity will probably something around 1/2, not 1/3, but 1/2. So, every half of the values will probably smaller than the average. Well, that's just that's something that you could assume if the distribution of values inside the column A is somewhat uniform. So that might be a more clever estimate at this particular case. In this particular case, the system does not know about this particular estimate. It simply applies its heuristics here, as you can see. Well, indeed, when the query has been executed, we see that indeed half of the rows could qualify here. But, well, this is after the fact. Before the fact, we apply heuristics. All right. So, well, now it's just instantiating the well-known formulas. The startup costs are now non-trivial. This accounts for the startup cost of the subquery. And indeed, as you can see, the startup cost of this query is non-zero. Then there would be the CPU run cost and the disk run cost. All of these we have already seen. Well, if we add all of this stuff up, then we end up at 46,192, and this is exactly the cost estimate value that has been assigned by PostgreSQL. All right. Yeah, right. Let's switch on index scan and bitmap scan again. All right. So that's it. That's all I wanted to say about the cost estimation of sequential scan. Right. So actually a rather simple setup that tries to take into account the different ingredients that make up a sequential scan, and try to incorporate the basic configuration parameters of the cost model to arrive at sensible space dollar values. All right. So thanks for your interest. There will be one final video where we repeat this particular experiment and the discussion for the index scan operator. I'm looking forward to discuss this with you. Stay tuned for that last video. See you then. Bye bye.